Hello, my name is Vincent Kennedy. This is going to be my submission for Part B of the final project. In this video, I'll be going over how to create wing type 2B, where the wing will have an aspect ratio of 10 and a tapered ratio of 0.6 with a root chord length of 1 meter. I'll be showing you how to get the geometry for this and how to plot CL versus angle of attack, CL versus CD versus angle of attack, and then CD versus angle of attack. I'll also be helping find to get local lift coefficient, induced angle of attack, and induced drag coefficient at 5 degrees of angle of attack. So to start off the process, we go and open up XFLR5 and click Module. Go into Direct Foil Design and then click Foil and Naka Foils. For this project, we'll be using a 2415 design, and that'll be specified in the project. And then this number of panels is essentially just your resolution. And so it could be 100, 250, 300, even higher. For this project, I did 250, but for this example, why don't we do 300? And click OK, and then OK again. Now we have our new foil. Next, we're going to have to start by doing a batch analysis of this foil before we can get into make the wing. So click this X foil direct analysis, then go into analysis and batch analysis. In this page, you're going to want to do some editing to this list of RE values here. You're just trying to list all the RE values that your wing might be in. And so you have to make sure it contains the Reynolds number that your wing has. For this project, the wind speed is 50 meters per second, and so we're going to need a higher RE than just the 3 million. The max we'll be getting is 3.333, and so we need that number here, and then we'll also need a number past that to get all the data points we need. So make sure you add those by clicking this button and then an insert after. You do this twice and then edit the second number into 3.333. Then make sure polar type is T1. Force transitions needs no changes, and analysis range, you make sure that it's an alpha. And then for this project, you could have it as -5 to 15 because that's the range we're looking for. I just chose to do -6 to 16, so we get a couple extra data points, so we're not missing any of those 5 degrees or 15 degrees. So make sure you have from 0 unselected, and then click Analyze. Wait for this to process. It should only take a couple of seconds. It should say Analysis completed, and then you just click Close. This is all our data for this foil, and then from here we can now begin working on our wing design. So we go into Module again, Wing and Plane Design, then click Plane and define new plane. So we can call this one, we can just call this TR_0.6, as that's the one we were told to make in the video. We could deselect elevator and fin, as we're not doing this, we're only analyzing the wing, and then we can go and click Define. First off, we can change the foil to be our NACA 2415 at the beginning and end of the wing, and we can begin to create our tapered wing. So to do this, we can just have to specify our root chord length at the center, which will be this length right here as 1 meter. And then we need to create the end chord length, which is just the taper ratio, 0.6. As the ratio between 0.6 and 1 is indeed 0.6, our taper ratio is 0.6 as specified in the project. However, this is not all we have to do. We do have to edit the offset so that our wing is symmetrical along one axis. So to do this, we are going to take 1 minus this 0.6 to see how much we took off, and then divide that by 2. So 1 minus 0.6 is 4, or 0.4. Divide that by 2, you get 0.2. Those offset right here, you just type in 0.2. And now we have a nice symmetrical wing. Now all we have to do is click Save, and save again. And we have our geometry for the wing created. The next step is to find CL versus angle of attack. So to do this, we hit Analysis, define an analysis, make sure this type is type 1 with fixed speed. You can change this free speed velocity to 50 meters per second right here, and go into Analysis and make sure you're selecting LLT wing only analysis method, as that's the type we use for this project. So go back to polar type. Now we can see that our maximum is indeed 3,330,000, and so we just click Save. So now we need to collect data points from -5 to 15. So we go into Analysis Settings, select this, type in our -5 and our 15 right here, and we're supposed to be doing this in increments of 1, so that's also 1, and we just hit Analyze. And here we have our data points for all our angles of attack. And so now we can begin finding our analysis of CL versus angle of attack. So we go into Polar View, and we use these charts here. So as we can see, we have our CD versus alpha, our CL versus alpha, and our CL versus CD alpha, as well as our efficiency versus alpha. So these are all the ones we need in this project. However, if these didn't show up when you open this page, all you have to do is hit right-click, Current Graph, define graph settings, and select the value you want to find along the alpha axis. So we wanted CD versus alpha, so we can just hit OK, and we still see all these needed graphs we needed for this video. So next we want to find our local lift coefficient, induced angle of attack, and induced drag coefficients at 5 degrees. So we go over to this panel right here, find 5 degrees, click that, and go into Op Point View. And here we have it. This is our graph. So all we have to do to find local lift coefficient is right-click, Current Graph, define graph settings, and click Local Lift Coefficient, then click OK. This would be our lift coefficient for our wing of a taper ratio of 0.6 and an aspect ratio of 10. We could also do the same thing to find induced angle of attack. So again, define graph settings and induced angle. Click that. Here's induced angle of attack. And then current graph, define graph settings, and induced drag coefficient. There we are. That is the last piece of information we needed to find for this video, as specified in the project, the geometry. We went over that. We also went over CL versus angle of attack, CL versus CD versus angle of attack, and CD versus angle of attack, as well as finding local lift coefficient, induced angle of attack, and induced drag coefficient at 5 degrees angle of attack. So that'll be it for this video. Thank you for watching, and have a great day.